Okay, and our final speaker for today, Bo Sundborg from Stockholm University, who'll talk about black holes in higher spin AdS4.
Okay, now you can hear me? Yeah. First, I'd like to thank the organizers for this great meeting and for my chance to present this work here. Black holes in higher spin AdS4 CFT3. The reason I wanted to talk about this now is that it's a problem. So I'm going to try to address that problem. And you'll see, I'll show you what it is. But there's also an opportunity in that duals of this strange gravity theory, higher spin theory, are very simple conformal field theories, which may give us the opportunity to look at black holes and understand them in a simple model, not only extremal black holes, but sort of general neutral black holes and perhaps their microstates. So that's the idea. Let's see if I can move this forward. Yeah, you may have heard lots of misgivings about high spin theory, Vasiljev high spin theory, whether it makes sense or so in the bulk. My attitude is that since there are partial results, at least, on holographic duality, we can use those to define sensible bulk quantities, even if we don't really know how to handle the bulk formulation. I certainly don't. There are high spin experts that know much more, but I find it very difficult. But I'm not going to use it directly. Right? I don't think it's necessary for everything, at least. All right. So since this is an ancient subject, I thought I had to review a little bit of the background. For me, this history starts with symmetry, high energy symmetries of string theory, actually. As Lawrence mentioned yesterday, that high energy scattering was studied by Gross and Mende a long time ago. And after that, Gross extracted some ideas about short distance symmetries. Now, a much more simpler way to approach it became available with the idea that you could have strings in AdS where you have an intrinsic length scale. Then it makes sense to take the tensionless limit, comparing the string length to the AdS scale. And then if you do that in holography, oops, is this? Yeah, it's a very weak one, but here. If you do that in holography, you will have a theory of free fields in the boundary. And free fields in the boundary means that there are higher spin conserved currents like this. Conserved just because of the free equations of motion. Those higher spin currents in the boundary correspond to massless higher spin fields in the bulk, which then would be sort of higher spin sub-theory in tensionless string theory. So that's the context where it started for me. Now, the actual higher spin theory was formulated long before that, in the late 80s, and only includes one higher spin, a single spin 2, a single spin 3, etc. So it's a very simple spectrum compared to the spectrum of full string theory. And to find the conformal field theory corresponding to that is actually much simpler than a matrix theory, which is what Young-Mills theory is. In essence, it's an ON or UN vector model. Very simple. And that is sort of part of the hope of this model. You can make use of that simplicity. Now, 3-point interactions were also matched eventually a bit later than the conjecture of the duality. And they were matched between the Owen model in the boundary and the bulk high spin theory. All right. It's just symmetrization. And there are you can determine the coefficients so that these things are actually, you know, traceless and conserved, etc. It's just the formal expression. All right. Now to discuss black holes, in holography it is customary to because the history is that Witten proposed this duality between AdS black holes and the deconfinement transition. And we'll see where it sort of comes from thermodynamics. The transition was known already in AdS by Hawking and Page. And what connects this thermodynamic story to the higher spin or models or tensionless string theory was that it's kind of easy. This is the kind of expressions you get to find the deconfinement transition in free models on the sphere. And these are the kinds of expressions that are involved. I will not go into details of these expressions today. It's late. But the same kind of technology was then used by Schenker and Yin in a beautiful and very annoying paper. Now, note that in this case, the phase transition for vector models is not constant. It scales as a square root of n, which is sort of the cause of all of the trouble. Right. So what can we do? Well, we can quite easily find the high temperature regime on the sphere. It's simply a black body gas, a free gas on the sphere. At very high temperatures, it's the same. It's the same as in flat space, and famously, importantly, and everything, it matches the behavior of the asymptotic high temperature behavior of black holes in AdS, Schwarzschild AdS black holes. They have automatically this holographic form. So you could think of AdS black holes as sort of the precursors of holography. Yeah, and there is this slight difference here in the end dependence, which indicates, suggests that what you should compare the Newton's constant with in the dual dictionary. Right, okay. Now, what's annoying about the Schenker and Yin paper, the paper is technically beautiful, but what is annoying is that it's more or less the results. I don't like them. They can still be true, of course, even if I don't like them. But I think there's what they essentially say, there's a lot of text here. What they essentially say is that higher spin duality does not really work as we expect duality to work, which could be a problem with the actual theory, or could be a problem with holography. Or it could be perhaps a problem of the interpretation. I will try to take that latter perspective, but it's not easy. So let's try to squeeze things into an interpretational problem. All right, and then you get maybe different results. But I admit it will not be totally convincing. However, there are still lots of things to say about this system, which I think will be important, whatever the eventual conclusion is about the interpretation. All right, so another important but not very well advertised result of Schenker's and Yin's is that they find and they discuss composite operators, invariance operators that are very, very massive. The dimension will be of this scale. And the reason that they are massive is that you need to contract the fields, which are n vectors, n component vectors, with the Levi-Civita symbol. So you need n of them. And this antisymmetrics, you need to have a number of derivatives on the fields in order to get something non-zero. Schenker and Yin also very nicely gave the partition function for these interesting, very heavy, and very many states. But then they didn't do so much more with them. I'm going to repair that now and tell you more about them. All right, so we'll come back to this. And then I will explain to you why I'm so annoyed by the results of Schenker and Yin. Because their results notwithstanding, we tried to extract physics, or maybe to sort of probe their results, try to extract physics out of these systems, free field theory in the Owen model, free fields in the boundary, which would correspond to high spin symmetric gravity in the bulk. How do you probe it? Well, you just calculate correlators and investigate their properties, try to interpret them in terms of gravity. And so this is in spirit similar to what Romuald was talking about. And there are a number of observations that we made, and they all seem to be fairly consistent with the idea that this is actually something very much like black holes in the bulk. So we have two statements. The high temperature phase of higher spin theory is different from that of string theory or gravity. And the high temperature phase of higher spin theory is similar to that of string theory and gravity. Oops, time passes. Okay, there's time dilation. So takeaways here. I was expecting this. All right, so first, there are these interesting states, numerous and super heavy, and they signal the confinement transition. There is, and that I will not have any time to say anything about, possibly a new interpretation of the units to use, how you should look at the AdS scale. All right, the thermodynamics of these states. Quickly, here they are. Because of this antisymmetrization, you effectively have a gas of n free fermions, in quotes, which means that these are actually like white dwarfs or these states. They're fermion gases. They are like white dwarfs or neutron stars, only that the fields, the particles, are massless particles on the sphere, on the two sphere. So it's like a hologram. It is like a surface of one of these objects. Anyways, the ground state is very, very heavy, growing rapidly with n. And in this case, I've drawn here, it happens to be a scalar, but in general, depending on n, whether it's a square or not, they are very highly degenerate and have extreme degeneracy. So they are like thermodynamic objects suitable for that. They are also kind of intriguing from the perspective of bulk higher spin theory, because you can calculate 3-point functions, and in general they are non-zero with the higher spin currents, means that they couple to massless higher spin fields in the bulk. And this is just like the boundary corresponding duals to Didenko-Vasiljev higher spin black holes, how they should behave. So this you can probably match to that in some way. All right, you can do standard thermodynamics. It's nice when you have fermions to use the grand canonical ensemble. And here it is. Quite unremarkable. Entropy, internal energy, and free energy. There's something interesting here in the free energy, which is what? It has a zero at a certain temperature, which is very, very close to the critical temperature of the full gas. This is just, remember, this is just one state. It's just of a very complicated object, like a star or a black hole or something in the higher spin theory. That the free energy vanishes is analogous to what happens in the Hawking-Page transition at the transition temperature, when free energy of the bigger black holes vanishes, and in principle can dominate thermal ensemble. This could happen here as well, obviously, depending on the processes. So the picture is that this is actually like the Hawking-Page transition, but this temperature is slightly below the deconfinement transition. So that's why I would call these vector baryons like condensation nuclei for black hole formation. Eventually, as you increase temperature, first these objects are favored thermodynamically, and just after the slightly higher temperature, you reach the deconfinement transition, and black holes or something like that would be able to condense. Well, this is the story of finding units. I have 1 minute. All right, I can tell you one more thing. All right, so the idea is you can, assuming that the largest black holes are AdS4 child, like at leading energy, next to leading energy when you increase temperature. And also that the largest high spin black holes are this one. Also that the largest high spin blacks are dual to the high temperature equilibrium of vector models. A simple, very natural assumption is if it weren't for Schenker and Yin. Well, if you then calculate the leading order mass and the next to leading order mass when at high temperature, you can see that they depend on Newton's constant and the AdS scale. So in principle, you can use these values to observe, compute Newton's constant and the AdS scale. So let's calculate them in the boundary and then compute G and L. Okay. As a non-trivial calculation involving all of these integrals over eigenvalues that I showed you in the beginning, but it gives you something. And what it gives matches perfectly what I wanted. I didn't know this, but it matches what I wanted, namely that the critical temperature is actually at the AdS scale. If you observe the AdS scale and Newton's constant by this way of looking at the sort of semi-classical limit of black holes, assuming that they are black holes. Unfortunately, perhaps, it gives a very strange result for Newton's constant. So this is why I'm not quite happy with this yet, even if on all other accounts it satisfies my wishes. All right, I think I must have covered everything and got a bit over time, so thank you for your attention.
Thank you. Questions?
A possibly naive question, but you said that the ground state scaling dimension scales within like n to the 3 halves for this heavy baryons. But you know, from a very naive analysis, I would have thought they would have gone like n squared, because the number of derivatives on let's say this scalar quarks can never be equal. So they would be at least, you know, like 1 plus 2 plus, you know, because of the derivatives, like it should go like n squared.
No, I mean, that's the first estimate you would do. I agree completely.
Yeah.
The reason that you can go a bit lower is that you know, you have several directions to so you don't necessarily have, you can have momenta in all the directions, so you fill the levels more slowly. I mean,
I see. Thank you very much.
More questions? Is there a similar story for AdS5?
Is there a similar? Yeah. I realized that the other day. Just so I had to quickly sort of do the same computation for the sort of tensionless limit, which would correspond to this story for matrices, which is the appropriate for AdS5. Then you have the Young-Mills. I could only do the scalar toy model of this, and I couldn't completely do it, but because the contributions from to the corrections next to leading order in temperature are quite complicated, actually. So, but it looks like the result there is the expected one, that the AdS scale does not change with n, and the coupling is 1 over n squared. Newton's constant is 1 over n squared, as you'd expect in a matrix model. So, I mean, a sort of a test of this crazy way of measuring the cosmological constant. It seems to work.
Okay, if there's no further question, let's thank Bo again.